Swayam Prabha. Digital India. Educated India.
Here's another kind of more profound kind of statement. Every positive integer has a prime factorization so that's to say it can be written as a product of some bunch of prime numbers. So all of these pi are prime. Okay? So I'm not right now proving that it's a unique factorization. I'm just saying there exists a factorization. Okay? So the base case, and I'm again not formally defining what primes are, or I can tell you, number is prime if you cannot, it's a positive integer greater than or equal to 2, and you cannot write it as a product of two integers which are strictly greater than 1. Okay, and the smallest prime is 2. So indeed, n equal to 2 I can write as a product of just one prime, p1. The induction step is to say that suppose up to, for any k greater than 2, right? Greater than or equal to 2, I need to show this. Suppose for all n less than or equal to k, it is the case that n has a prime factorization. Then I would like to show that k plus 1 also has a prime factorization. So remember, again, the hypothesis is not just that k has a prime factorization. I'm saying all numbers up to k have prime factorizations. Okay, then I would like to prove that k plus 1 is also has a prime factorization. And I would like to prove this, it's missing here, I should say I can prove this for all k greater than or equal to 2. Okay, so there are two cases. If k plus 1 is already prime, then I'm good. Then it is the prime factorization. It has a way of being written as product of one prime. And the other case is if it's not a prime, then by definition of not being a prime, it means there is some integer that divides k plus 1. There is some integer a greater than 1, and it has to be less than or equal to k, the way multiplication works. You cannot multiply a number and get something smaller than it, multiplication of integers. So a is something which is at most k and strictly greater than 1, and it divides k plus 1. What does it mean to divide k plus 1? I can write k plus 1 as a times b. Now here is the thing. I don't know anything about this a. It may be prime, may not be prime, right? So all I know from the definition of not being a prime is that there is some integer a. But I do know that that integer a is less than or equal to k, and same with b. They're both integers less than or equal to k. They're strictly smaller than k plus 1. So I'm going to use the induction hypothesis that a and b themselves have prime factorizations. So here it's important that a and b, they're not equal to k. They are not just 1 less than k. There are some 1 less than k plus 1. There are some, potentially much smaller integers. And but my induction hypothesis tells me that every integer, every positive integer up to k, do have prime factorizations. So in particular, these a and b do have prime factorizations, and I can, suppose their prime factorizations are p1 to ps and r1 to rt, then I can just concatenate those things to get a prime factorization for k plus 1. Okay? So there's just notation to say these q1 to qu are actually just p1 to ps followed by r1 to rt. As I said, I didn't prove unique factorization, but that is also something that is true, and we'll get to it later in the next section of the course. Okay, so an important thing, you probably noticed that I had to be careful about the ranges for which I stated the induction hypothesis. And if I'm too sloppy, I'll end up being, proving or claiming proofs for things which are wrong. So here is an example of a claim. It says every non-empty set of integers has either all elements even or all elements odd. This is of course false. I can take a set of integers, say 1, 2, and it's not neither all positive, all odd integers, nor all even integers. So this is a statement that's probably false. But nevertheless, let me go ahead and give you a bogus proof. So the proof goes as follows. Let's take we are going to induct on the size of the set. So the base case is when that n, the size of the set, is 1, then there's only one element in the set, and it is either all even or all odd. Okay, so that statement is true. Nothing wrong with that for size 1 sets. And for induction, I'm going to say, okay, I'm going to prove that for all k greater than 1, suppose all, and this weak induction even that I'm planning to use. So suppose you have all sets of size equal to k satisfy this property that they're all even or all odd, then it holds for elements of size s equal to k plus 1. And I'm claiming this, I'm going to prove this for all k greater than 1. Okay. In fact, I'm going to skip over the 2 bullets here. You can read them. This is actually a true statement, and this is a valid proof for this. Okay, for all k greater than 1, I can prove this. That if sets of all subsets of size k have they're all of the same type, then all subsets of size k plus 1 are also of the same. So then what's wrong? What went wrong in my proof by induction? Nothing wrong here. Well, what went wrong is the fact that I'm proving this only for k greater than 1. And if that's what I'm doing, I cannot bootstrap the base case. So just to make it clear, here is going back to the table we had from the previous clip. What I proved is the base case, P1. And I proved for every k greater than 1, pk implies pk plus 1, meaning I proved P2 implies P3, P3 implies P4, and so on. And this wouldn't let me conclude anything. I cannot conclude P2. If I could conclude P2, then it would have let me conclude it for all integers n. But unfortunately, P1 doesn't imply P2, and I have not proven P2, right? So that's the thing to be careful about when you're making when you're choosing your base cases and your induction step. They should match up. They should line up so that in this table you should be able to have one row where the base case has been proven and the induction step yields the corresponding implication, pk implies pk plus 1. Our last example for proof by strong induction relates to this game called NIM. It's a game involving 2 piles of matchsticks, and 2 players, Alice and Bob, take turns removing matchsticks from the 2 piles. So initially both piles have equal number of matchsticks, and at every turn a player, so Alice goes first, then Bob, so they take turns, and in Alice's turn she must choose one pile and remove an arbitrary number of matchsticks from that pile, but she should remove at least one matchstick. Okay, and then Bob chooses a pile. He can choose either pile and remove an arbitrary number of matchsticks from that pile, and they keep going until all the matchsticks are gone. And the player who removes the last matchstick wins the game. Okay, so here's a claim that in this game, the second player, so Bob, has a winning strategy. Okay, so winning strategy means no matter what moves Alice makes, if Bob follows the strategy, he will win the game. By the way, every 2-player game which is guaranteed to terminate in a finite number of moves and not have a draw or tie, it's guaranteed that one of the players has a winning strategy. What we're saying here is a little more than that. We are saying no matter what the starting number of matchsticks are, so for each starting number of matchsticks, it's a different game, right? So in all of those versions of NIM, it's always Bob who has a winning strategy. Okay. And actually, we'll prove something a little stronger than just saying Bob has a winning strategy. We'll actually give a winning strategy for Bob. So here is the claim we are going to prove, that if Bob follows the strategy of, so at the end of his turn, he'll make sure the two piles have equal number of matchsticks. Okay. So if he follows this rule, he will be able to follow this rule until he wins the game. So that's a claim we would like to prove, and we will prove that by induction. So we'll induct on the number of matchsticks at the beginning of the game in each pile. So remember, both piles have the same number. So let's call that the size of the game. So we'll induct on the size of the game. For n equal to 1, it's pretty simple. So Alice, no matter what Alice plays, right? But Alice is only essentially only one way to play the game. She can choose either pile, but then the pile has only one matchstick, so she has to remove it. And then Bob's strategy tells him to remove the other matchstick from the other pile, and he wins the game. Okay, so n equal to 1. If Bob follows the strategy, I mean, it's not like there was much strategy for Bob either, but following this strategy, Bob will win the game. How about the induction step? So we're going to prove that for every integer k greater than or equal to 1, if it is the case that for games of size at most k, the strategy makes Bob win, then for games of size k plus 1 also, this strategy would make Bob win. Okay, that's what we're going to prove. So we need to prove that, so fix a k, make this induction assumption hypothesis, and then we would like to prove that if you have a game of size k plus 1, if the game is of size k plus 1, then the strategy will make Bob win, no matter what Alice follows. So depending on Alice's strategy, I'll have two cases. So depending on what Alice's first move is, I'll consider two cases. The first case is that in her first move, Alice comes in and picks a pile and empties it out. So she takes all k plus 1 matchsticks from that pile. Well, then Bob's strategy says he has to empty out the other pile in his turn, and then he wins the game. Okay, so that is one case. The remaining case is that she doesn't empty out any pile. So she comes in, picks a pile, and removes some j matchsticks from it, where j is strictly less than k plus 1. And remember, j is at least k. So j is in the range 1 to k. Okay. And then what would Bob do? Well, his strategy says he has to make the other pile balanced. So he will come in and remove, also he'll remove j matchsticks from the other pile, so that at the end of his turn, both piles have k plus 1 minus j matchsticks left. Okay. Now, the number of this number k plus 1 minus j could be anywhere from, so if j is k, then this is 1. If j is 1, then this is k. So it can be anywhere from 1 to k. Okay, and this is where it was useful to make our induction hypothesis the strong, induction hypothesis for strong induction. Okay, so we assume that for games of all sizes, in the range 1 to k, the strategy will make Bob win. So now whatever we are left with, the remaining piles, they look like the start of a game of size, something in the range 1 to k. And therefore, we can apply the induction hypothesis on the, the state of the game currently, right? So it's like we are starting a fresh game of NIM with strictly less than k plus 1, or in other words, less than or equal to k matchsticks. And the induction hypothesis tells us that Bob is going to win that game. Okay? And so therefore, he's going to win the full game, because the full game is just going to have the same result as the game after the first move, right? So that's it. That's a proof that this strategy would make Bob win. And the important point here was that we really relied on the strong hypothesis, strong induction, to reduce the game of size k plus 1 to a game for which we already know something from induction. All right, so that's it for now, and do keep working on more exercises using induction.